In this video, we will learn how to characterize and trace a battery ground fault. When tracing a ground fault, a low-frequency AC signal is injected between the side of the battery string that has the ground fault and earth. The path of the low-frequency AC signal is then traced. Before tracing the signal, we will first characterize it. This is done because the ground fault may not be the only path drawing the fault current. Since the test current is a low-frequency AC signal, capacitance in the system can also draw current. Cables have capacitive properties. They have a center conductor and shield separated by an insulator. This creates a capacitor. The longer the cable run, the more capacitance there is, the higher the leakage current. We want to be sure to trace the ground fault and not the leakage current. Before starting the trace, we need to know whether or not the ground fault is positive or negative. We will acquire this information off the ground fault monitor or use a DMM to determine which side of the string has the ground fault. Set up the transmitter. Set the power switch to off. Set the output switch to off. Set the voltage knob fully counterclockwise. If the BGFT is a C model, then we want to set the voltage switch to the 15-volt position. Verify all the Wheatstone bridge knobs are in their blue positions. This is the battery ground fault simulator that simulates the battery string, the panel, and the ground fault. This is used to demonstrate battery ground fault tracing. Connect the transmitter's leads to the transmitter. Connect the transmitter's leads to the battery string. Since this is a positive fault, connect the transmitter lead with the red label to the positive side of the battery string, and the transmitter lead with the green label to earth. Never connect the transmitter leads across the battery string. You could blow the fuses. If your system has a ground fault monitor, it is recommended to disconnect the ground terminal of the ground fault monitor because the monitor can provide a false path to earth. Before beginning, be sure to check the receiver's battery by moving the switch to the battery test position and verify that the green lamp is illuminated. After verifying the battery condition, set the receiver to the ×100 gain position. Place the receiver's CT around the transmitter's red lead. Turn on the transmitter and wait for the ready lamp to illuminate. Turn on the output current by pushing the output button to the on position. Set the output voltage to between 10 and 15 volts. Now we will measure the total fault current, so note the current on the receiver. If it is in overrange, lower the gain setting on the receiver until a stable measurement is obtained. The fault is now ready to be characterized. Plug the feedback loop into the transmitter. Place the feedback loop inside the current clamp. This places the Wheatstone bridge in parallel with the fault current. With the Wheatstone bridge connected 180 degrees out of phase with the fault, we can tune the fault out. This allows us to determine the characteristics of the fault. Note the knobs on the Wheatstone bridge are labeled 1 through 6. Start with 1 and work through 6. While monitoring the receiver, start turning knob 1 on the Wheatstone bridge. Continue turning the knob until the reading on the receiver goes up or down. If it starts going up, stop and turn the loop around. This indicates you are adding capacitance in phase with the fault, which is drawing more fault current. If the reading on the receiver goes up no matter what direction the loop is in, this indicates there is little to no capacitance. So no matter what direction the loop is in, you are adding more capacitance, which is drawing more fault current from the transmitter. In this case, you can be sure the fault is purely resistive, and we can proceed with just tracing the fault. If the reading on the receiver is going down, continue increasing the capacitance, moving from knob 1 through 3. until the minimum value on the receiver is achieved. At some point, the value may start to increase. We want to adjust the Wheatstone bridge to achieve the minimum reading on the receiver. Once the minimum value is achieved using the capacitance knobs, now continue tuning out the resistance using knobs 4 through 6 until the minimum reading on the receiver is reached. Once the minimum value is reached, the resistive value of the fault and the capacitance of the line will be represented by the values on the Wheatstone bridge. In this case, there is 5 microfarads of capacitance on the line, and the fault resistance is 2 kiloohms. If the majority of the fault current drops when adjusting the resistance, the fault is primarily resistive, we can proceed and trace the fault. To trace the fault, we go to the panel and we measure the fault current in each circuit. We want to find the circuit drawing the most fault current. We will then trace this path to locate the fault. See what the total is on the receiver and take measurements on each circuit on the panel. There is no fault current on circuit 6. Therefore, no fault is here. The same is true on circuits 5 through 2. The entire fault current is on circuit 1. This indicates the circuit has a ground fault since all the current is on the circuit. This is the only circuit with the ground fault. So we are going to trace the fault down through circuit 1. We see the current here, so I move further down the line and we still see the current here. So I move further down the line. Now we don't see any current. This means the fault is in between these points. In this scenario, we have multiple faults that need to be traced. In this case, we can see our total fault current was 0.902. So now we are going to start looking for that current. We start on circuit 6, and note there is no fault current on circuit 6. So we go to circuit 5, and we see there is no fault current on circuit 5. So now we go to circuit 4, and we see there is no fault current on circuit 4. Now we go to circuit 3. Here we see fault current, but it is not the total fault current. So we go to circuit 2. We don't see any fault current on circuit 2. So now we go to circuit 1. Here we also see part of the fault current on circuit 1. We see the fault currents are divided between circuits 1 and 3. Circuit 3 has the highest fault current, so we will trace that circuit first. We trace circuit 3, and we still see the fault current here. We go further down the circuit, and we still see the fault current here. We go down the circuit further. Now we no longer see the fault current, so we know the fault is between these 2 points. Now, before continuing, this fault would need to be fixed. Let's assume this fault has been fixed. We still have another fault we need to locate. I know that fault was on circuit 1, and we can still see we have that fault. So we trace that fault through circuit 1, and we see that fault is between these 2 points. Now we can fix this fault. If the majority of the fault current drops when adjusting the capacitance, then there is a large amount of leakage current on the system, and we need to take an extra step to verify we are tracing the correct path. In this case, we note our total fault current is 0.451. We go to the panel and find what circuits have fault current. Checking circuit 6, we see there is no fault current, so we go to circuit 5, and again, there is no fault current. So we go to circuit 4, and there is no fault current here either, so we go to circuit 3. Notice we have some of the fault current on circuit 3. Now we continue on to circuit 2, and we see there is no fault current on circuit 2. So we proceed to circuit 1, and here is the rest of the fault current. So we know we have fault current on circuits 1 and 3, However, from our initial characterization, we know there is a lot of leakage current on the system. So now we need to determine which circuit has the resistive fault and which one has the phantom fault due to leakage current. To do this, we are going to reinstall our feedback loop. Now, we are going to see if the fault current on circuit 3 is capacitive or resistive. Circuits with high capacitance have high leakage currents, so we start turning the capacitance on our Wheatstone bridge. Note the receiver value goes up, so we want to flip the feedback loop around. Now we see the value going down. So we are going to tune it down to the lowest reading we can get. Now we go to the resistance knobs. We see we cannot reduce the reading any lower. The reading just increases. Our capacitance is 5 microfarads, and the resistance is over 200 kiloohms. This circuit is purely capacitive and just drawing leakage current. This is what we call a phantom fault. It is due to long cable runs. If we were to trace this circuit, we would trace all day and never find a fault. We now go to the breaker with the next highest level of fault current and characterize that breaker. In this case, that is circuit 1. So we place the CT with the feedback loop on circuit 1. Now, we will increase the capacitance on the Wheatstone bridge. Notice the reading of the receiver is going up, so we turn the feedback loop around. We see now it goes up with the feedback loop in either direction. This indicates there is no capacitance on this circuit. In fact, if we keep going down through the capacitance dials, we can see the value just continues to go up. With the feedback loop in either direction, we are still adding capacitance. This is because there is no capacitance on the circuit to tune out. Now we go to the resistance knobs and notice the reading is going up. We have the feedback loop backwards, so we turn it around. Now we see the resistance reading going down. We continue tuning out the resistance until we reach the minimum value on the receiver. Now we see the fault resistance value is 2 kiloohms. We now know that the real resistive ground fault is on circuit 1. Now we can trace circuit 1 and be sure we will locate the fault. We always want to characterize the fault before tracing it. Many times faults will be mostly resistive and we can go ahead and trace them. However, in cases where there are long cable runs, the capacitance from these cables draw leakage current, and this produces phantom faults that can cause us to trace all day and never find it. This is why the BGFT method of characterization will save you time and frustration. Megger, helping you to power on.